Hello everyone, my name is Yasaswin and together with Pishayanon, we proudly present our senior project FiT-AI trainer. So let's start with the problem and motivation behind this project. More and more people are starting to care about their health, but with busy routine, many people prefer to work out at home. However, relying on workout video to exercise can lead to injuries, but hiring a fitness trainer can come with high costs too. So what is our solution? We develop a mobile application that acts as a personal fitness trainer like in your pocket. It helps people work out at home with better guidance and more confidence. No need for expensive trainer, no marketing if you're doing it right or wrong. The application target for core feature from tagging, tempo tracking, real-time feedback, and lab counting. Now, who is this app for? Our target stakeholder are three groups: beginners who have little to no fitness knowledge, home workout enthusiasts who already exercise at home and want a better result, and fitness trainer who can use this as a supplementary tool for their client. So let's look at the research that inform our project. The first related is it demonstrated a machine learning based mobile exercise coaching application that provide a real-time feedback to a CNN. The results show significant improvement in user physical health metrics, validating the concept of AI-powered exercise coaching. So next one is a comprehensive analysis of post-estimation models. Among all models evaluated, MediaByte Pro stood out as the best choice for mobile fitness hacking, offering 3D coordinate, 30T landmark, and high applicability for remote fitness training. Next is a workout classification system using a CNN in an assembled learning framework. The pipeline use media pipe to extract post landmark, then apply a multi-layer perceptron model to classify exercise type, achieving strong accuracy across 10 exercise categories. Next is the post estimation for correcting exercise posture. The system computed joint angles and range of motion to determine if an exercise was performed correctly, a key installation for our feedback mechanism. Next is the comparing iron and Tizen approach for skeleton-based action recognition. The results clearly show that Tizen-based model outperform LSTM-based one in accuracy, speed, and model size, which led us to adopt TCN model as the backbone for our dynamic workout models. Now let me walk you through the our system overview. The software workflow is straightforward. First, the user select a workout and they perform the exercise in front of the camera. The AI detect the workout form in real time, and finally, the AI generate feedback to both text and voice. Here's a high-level overview of our tech stack, covering the front-end, back-end storage, data processing, AI, ML, testing, and CI/CD layers. We'll go into more detail on how this all connect when we reach the software diagram section. So now let me explain how our AI system works. The pipeline starts with pre-processing pipeline, which feed into two parallel model pipeline: the dynamic pipeline for moving exercise and the isometric pipeline for static exercise. Both ultimately produce feedback to the user. Now let me walk through the data collection. We focus on two dynamic exercise, which is squat and lunge, which contain movement that involve continuous motion to multiple phases, and two isometric exercise wall sit and plank, which are the exercise where the user hold a static position under muscle tension. For dynamic exercise, we label each movement into two phases: the eccentric phases where the muscle lengthening under load, which are when you're going down in a squat, and the concentric phase where the muscle contracts like standing back up, because each phase it consists of different inclined posture. For example, in eccentric can contain feet too wide and feet too narrow, but in concentric it can contain knee not deep enough and rounded back. Here's how our data set is distributed. For squat, we record 150 correct video and 30 video incorrect cast per incorrect cast. For lunges, 150 correct and 50 per incorrect cast. For wasted and plank, 100 correct and 25 to 50 per incorrect cast. This gives us a well-balanced data set across all exercise. Now let's talk about the pre-processing pipeline. So, so here's our overview diagram for pre-processing pipeline, and we will go deep into it. So for frame extraction, we use OpenCV to extract individual frame from each video, converting the temporal footage into a sequence of image frame. For post estimation, each frame is then processed using media pipe which detect 33 body landmarks and output their 3D coordinate with confidence scores. But not all 33 landmarks are relevant for every exercise. For this example squat, we focus on 8 key landmarks: the left and right shoulder, hip, knees, and ankles, the joint most critical for detecting squat form. To make the model robust to different camera distances and angles, we apply body relative normalization using the hip width as reference scale. This ensures consistent features values regardless of how far or close the user is to the camera. From the normalized landmarks, we compute T types of features, angle between T landmarks using the cosine formula, distances between two landmarks using Euclidean distance, and relative distance ratios to capture proportional body relationships. For the mixed exercise, we use a two-stage pipeline. First, a TCN phase model processes the feature sequence and assigns a phase label to each frame. After temporal resampling, the phase label sequence is passed to the TCN form model, which classifies the exercise form and generates feedback. So the phase detection model takes a sequence of frames as an input, processes them to a temporal convolution network, and output a phase level for each frame, identifying whether the user is going down or coming up in the movement. Next is the form detection model, then take the phase level sequence and classify the form using another TCN, outputting a form level such as correct, needing, or not deep enough for squat. For isometric exercise, the approach is much more simple. The feature sequence go to the statistical aggregation, then directly into a logistic regression model to classify the form and produce feedback. So we don't need surface detection. We simply aggregate the frame features statically and apply a logistic regression model to determine if the form is correct or not. So here's our model result. Our model achieved above 89% accuracy with the exception of Pang at 81.74%, which is expected given the subtlety of its post variation. Overall, the models perform well across our four exercises.
We will talk about the software part. It will cover the software architecture, screen in application, demo of application, and the CI/CD. This diagram shows the software overview and tech stack that we use. On the front end, we use the Swift to build the iOS application and AV Foundation for the camera and text-to-speech service. On the back end, we use the Python with the fast API to handle the WebSocket, and we store data with the file-based authentication and file-based file store. And the data processing pipeline, we use the MediaPack, OpenCV, Pandas, and NumPy. To prepare the input for the AI model, we use the PyTorch for TCN and scikit-learn for the logistic regression. And in the testing part, we use the SonarCloud for scan the code quality and PyTest for test the unit test and API testing. And CI/CD, we use Docker with the Hugging Face Space to deploy the backend and GitHub Action for the create the CI/CD pipeline. This diagram shows the structure of our application. The front end, we use the MVVM architecture to separate the UI from the business logic. The view layer handle the UI while the model layer manage the data and store it in the file-based file store. The view model manage the workout state and connect to the camera service to capture the frame and stream them to the backend over the WebSocket for the real-time communication. On the backend, the frames are processed by the session manager and passed to the AI pipeline to generate the feedback, and it sends it back to the front end. The view model will update the UI and trigger the text to speech for the voice feedback. Before we jump into the demo, let me quickly walk you through the e-screen in application. The login screen is the entry point of application. Users sign in with the Google using the file-based authentication. After login, user can edit and save the information on the profile management screen. This data is synced directly to file store. This is the home screen, which is the main dashboard of the application. It will show the workout program as a card, and user can choose exercise based on the difficulty that they want. Right now, the difficulty is not designed in a fully professional way because we made it simple for the demo. In the future, we can improve it to be the more professional by working with the expert. And then when user select each program, it will navigate to the workout list screen that display all exercise in program with the required rep and hold duration for the each exercise. When click start workout, the application will show the animated port demo to help user understand the correct form. It also provides the voice guidance to support the proper execution. And it have the workout preparation screen to check the two things. The first is full body visibility and the second is environment lighting. If the user is not fully in the frame, the app will tell them to adjust the camera. If the room is too dark, it will tell them to adjust the light. When everything is ready, the user will move to the main workout screen, which is the core of the application. In the main workout screen, the app will stream to the server and the server will count the correct and incorrect rep and provide real-time feedback as a text and voice to guide the user during the workout. After completing the session, the workout result screen will show the full summary, including the correct and incorrect rep, what went wrong, and tappable mistake keep. User can tap on any mistake to watch a short video replay of what happened and have the detail why it was incorrect. And this is the history screen to show the user workout completion history with a weekly calorie chart. They can have any past session to see the full breakdown. It will show the detail like a workout summary. We will show the demo of our application. When you open the application, you will see the workout program. You can select any of it that you want. In this demo, the system support for exercise was it support plank lunges. These exercise are selected to the showcase what dynamic and isometric movement.
Session started. Wall sit. Stand sideways to the camera and make sure your full body is visible. Keep your back against the wall. Lower down until your knees are about 90 degrees. Keep your body straight and hold the position. Adjust your camera to show your full body from the side. Please adjust your lights. Adjust your camera to show your full body from the side. Side view okay. Not deep enough. Okay. Back of wall. Okay. Past, squat. Face the camera and make sure your full body is visible. Slowly lower your body until your hips are at knee level. Then push back up to a standing position. Adjust your camera to show your full body from the front. Front, stand okay. Stand too wide. Stand too narrow. Stand okay. Good. Not deep enough. Knees in. Round back. Not deep enough. Good. Good. Past, plank. Stand sideways to the camera and make sure your full body is visible. Lower yourself down onto your forearms, keeping your elbows under your shoulders. Keep your body straight. Adjust your camera to show your full body from the side. Lower into plank position. Please start plank. Side view OK. Hips too high. OK. Hips too high. OK. Past. Lunges. Stand sideways to the camera and make sure your full body is visible. Step forward. Lower until both knees bend comfortably. Then push back to adjust your camera to show your side view OK. Please start lunges. Good. Good. Not deep enough. Torso lean forward. Not deep enough. Past.
When complete, you can see the full summary and can click on any typeable mistake to see and review the why your mistake. And you also hit the progress to see the history of the workout session, and it's like the workout summary session. You can click on any typeable to see the detail. Next, we will talk about the limitation of our application. Media pipe post estimate have the limitation with the asymmetric side view exercise, such as the lunges. It like the exercise that move the left side and right side not the same. For the lunges, when the step forward, body part can overlap and leading to the misdetect key point, which may cause the incorrect feedback for the lunges exercise. And next, we will talk about the testing part. We implement the automated test using the PyTest for test application. We have the functional testing cover the 105 test case or of test each part, and we have the API testing cover the TTT test case and all test part as well. And we also run the Sonar Cloud scan on the overall code base. The code quality gets part with the zero security issue, zero reliable issue, and a zero maintainability issue. Code coverage is at the 77.9%, and the code duplicate is only 3.2%. And the next is the deployment. For the iOS application, deploy to the App Store require an Apple Developer Program membership. It costs $99 per year due to the Discord, so we have not deployed it yet. However, the application can still be tested on the real iPhone directly using the Xcode. For the backend part, we use the Hugging Face Space to the host and run the AI system online. It provides the easy deployment and a quickly model update, and also stable environment for the demo. And next is the CI/CD pipeline. We set up the GitHub Action workflow to automate the run every time when code is pushed or the pull request. The pipeline starts with the unit test, API test, and then Sonar Cloud scan. If everything passed, the backend is automatically deployed to the Hugging Face space. The whole process takes around 7 to 8 minutes. Thank you for your attention.